Hello, and welcome to Section 3 of this course. In this section we are going to look at the following topics. First, we are going to start by talking about some essential topics pertaining to the theory of wireless networks. Next, we are going to provide an introduction to wireless frames. This will be followed by a brief introduction of the Aircrack NG Wireless Auditing and Penetration Testing Suite. Finally, we will look at how we can use Wireshark to sniff wireless frames. Since wireless penetration testing is a fairly practical subject, we highly recommend you to set up a lab to repeat the demonstrations shown in this course, in a safe and controlled environment. Most of the wireless networks in operation today are based on the IEEE 802.11 standards, usually marketed as Wi-Fi. Therefore, it is fundamental to have an intermediate-level understanding of these standards before we can start our journey of wireless penetration testing. Please note that as a course prerequisite, viewers should be aware of the basics of wireless networks. This includes having prior knowledge about the basics of the 802.11 standard and the communication process between wireless stations. Next, we are going to talk about basic RF theory, which will introduce wireless bands and channels. Finally, we will talk about the different wireless operational modes. This section has been included for the sake of revision, and might be too involved if you are not already aware about the basics of wireless theory. The IEEE 802.11 Working Group has published various standards related to wireless LANs. Some of the notable standards and the associated amendments are listed below. First is the 802.11 standard. This is the original standard for WLANs. It was based on 1 Mbps and 2 Mbps speeds in the 2.4 GHz radio frequency range. Next is the 802.11a standard, which was released in 1999. It increased the speed of WLANs up to 54 Mbps, utilizing the 5 GHz frequency range. Then we have 802.11b. This was an enhancement to the original 802.11 standard to support speeds up to 11 Mbps, utilizing the 2.4 GHz range. Next is the 802.11g standard. This amendment increased the speed of WLANs to 54 Mbps, also utilizing the 2.4 GHz frequency range. This is backwards compatible with 802.11b, and it is the most common type of WLAN in use today. Next is 802.11i. This standard was produced to enhance the security of WLANs, particularly addressing the insecurities introduced by the WEP protocol. Then we have the 802.11n standard, which introduced a significantly higher throughput for WLANs utilizing various cutting-edge technologies like MIMO, beamforming, etc. As of 2012, IEEE has released a new standard titled IEEE 802.11-2012, which rolls up all of the above standards and amendments into one unified standard, thereby superseding all of them. Other upcoming standards that should be interesting to follow are the 802.11ac and 802.11ad standards. The 802.11ac standard, once ready, will provide high-throughput wireless connectivity, theoretically reaching up to 1 gigabits per second, utilizing the existing 5 GHz frequency band. Similarly, the 802.11ad standard will provide extremely high-throughput wireless connectivity using the unlicensed 60 GHz frequency band. The Wireless Gigabit Alliance, or WiGig, is the organization developing and promoting the adoption of high-speed wireless communication, which includes standards like 802.11ad. Please refer to the WiGig wiki page for more details. The timelines and progress of these and other upcoming wireless standards can be tracked on the link displayed at the bottom of the screen. Now we are going to discuss the basics of wireless RF theory. Particularly, we are going to discuss wireless bands and channels. All of the previously mentioned frequency bands used by wireless standards are divided into channels, similar to how radio bands are subdivided into various frequency channels. The 2.4 GHz band utilized by Wi-Fi networks ranges from 2.4000 GHz to 2.4835 GHz. This band is subdivided into 13 channels. These channels are spaced 5 MHz apart from each other. The original 802.11b standard was based on DSSS modulation and utilized a 22 MHz channel width. This meant that there were 3 non-overlapping channels, namely channels 1, 6 and 11. The newer 802.11b standard borrows the OFDM modulation of 802.11a and has a 20 MHz channel width. This results in 4 non-overlapping channels, namely channels 1, 5, 9 and 13. Here, on the screen you can see a depiction of the various wireless channels in the 2.4 GHz range, including the channel width, and the 3 non-overlapping channels. Which scheme utilized on a particular network depends on a number of factors. One of those being the different regulatory standards followed by various regions. Each country defines the allowed frequency range in channels, maximum power levels, etc. So the availability of the non-overlapping channels would depend on the regulatory domain. Another important factor to consider would be channels currently used on the wireless network. For example, during a particular site survey you may observe that channel 6 is already utilized. In this case it might not make sense to use the new scheme, which utilizes channels 1, 5, 9 and 13. It would be better to stick with the old standard for non-overlapping channels. For more details please see the topic, List of WLAN channels on Wikipedia. Now we will look at some key wireless definitions. As we discussed in the previous sections, any device that connects to a wireless network using a wireless network card is known as a station, which can be of two types, namely clients and APs. The IEEE 802.11 standard defines two modes of operation for wireless networks, infrastructure and ad hoc. Okay, now let's look at some fundamental concepts pertaining to the various wireless operating modes. These concepts should also be firmly grasped before we move on. Collectively, a set of wireless clients and the access point they are associated with is known as a basic service set. BSSs are the fundamental building blocks of wireless networks. BSSs are identified by the MAC address of the access point serving them, which is called the Basic Service Set Identifier, or BSSID. At a minimum, each BSS running in infrastructure mode contains one access point and one client station. In the case of ad hoc networks, this could be two clients. Next is an extended service set, or ESS, which is a set of two or more basic service sets, or BSSs, connected to each other, which logically appear as a single BSS to the end station. ESSs allow wireless clients to roam within the wireless network without changing their Layer 3 IP addressing. The various access points in an ESS network are connected to each other by means of a distribution system, or a DS, which can be wired or wireless. Wireless interconnection of APs in an ESS is usually achieved by a protocol known as Wireless Distribution System, or WDS. Wired interconnection is managed by using regular wired uplinks to network switches, similar to physically switched networks. Please note that a set of interconnected BSSs serving the same ESS should share a common service set identifier, commonly abbreviated as SSID. Here you can see an illustration of the various terms we have just discussed. Now coming to the second mode of wireless operation, as defined by the IEEE wireless standard, an independent BSS, or more commonly known as an ad hoc network, is a collection of two or more wireless clients connected to each other without any central point of control. In other words, an ad hoc network does not contain any APs. Independent or ad hoc networks, as the name implies, are isolated and do not connect to any other BSSs. They are sometimes also referred to as peer-to-peer wireless networks. In ad hoc networks, the SSID is chosen by the initial client station that starts the network, and the other client stations can then connect to the ad hoc network using this SSID. The BSSID of ad hoc networks is still a MAC address, but is randomly generated. This concludes our current topic. Next we are going to talk about the flow of packets in the wireless connection setup process, followed by an introduction to wireless frames.